Hello everyone. Today my topic is deep learning based MIMO CSI compression. In this topic I have contained what is deep learning, introduction, system model, DeepCMC, distributed DeepCMC for two user, distributed DeepCMC for more user, and conclusion. So what is deep learning? It is a type of machine learning based on artificial neural networks in which multiple layers of processing are used to extract higher level of features from data. So deep neural network consists of multiple layers of interconnected nodes, each building upon the previous layer to refine and optimize the prediction or categorization. This progression of computation through the network is called forward propagation. The input and output layers of deep neural network are called visible layer. The input layer is where the deep learning model ingests the data for processing, and the output layer is where the final prediction or classification is made. For example, deep learning are virtual assistant, vision for driverless car, industries from automated driving to medical devices, face recognition, and many more. Now, introduction. Massive MIMO systems are considered as main enabler of 5G, and future wireless networks have ability to serve a large number of users simultaneously, achieving impressive level of energy and spectral efficiency. The base station in massive MIMO setting relies on downlink channel state information to fully benefit from the available degree of freedom and achieve the promised performance gain. In time division duplex mode of operation, massive MIMO system can exploit the uplink channel state information for downlink transmission, has channel reciprocity. On the other hand, frequency division duplex operation is more desirable due to the better coverage it provides. However, channel reciprocity does not hold in FDD, and hence downlink CSI is estimated at the user and feedback to the base station. The resulting feedback overhead becomes excessive due to massive number of antenna and user being served, and has motivated various CSI reduction techniques based on vector quantization and compressed sensing. So, compressed sensing based approaches rely on sparsity of the CSI data in the certain transform domain, which may not represent the channel structure accurately for many practical MIMO scenarios. CS-based approaches are also iterative, which introduces additional delay. The recent resurgence of machine learning, and more specifically deep learning technique for physical layer communication, deep learning based MIMO CSI estimation compression technique have recently proposed. The deep learning based CSI compression scheme called DeepCMC, composed of a novel fully convolutional autoencoder structure employing residual layer at the decoder for more accurate reconstruction in conjunction with quantization and entropy coding blocks, which allow us to approach the fundamental limits of compression more closely. Now, next is system model. We consider a massive MIMO setting in which a base station with anti-antenna serves k single antenna user utilizing orthogonal frequency division multiplexing over NC subcarrier. We denote by HK the downlink channel matrix of user K, and VK is the precoding vector used for downlink transmission for kth user. So received signal at K user is given by, where XK is data bearing symbol, ZK is additive noise vector. In order to design a pre-coding vector VK for efficient transmission, the base station requires estimate of the downlink channel state matrix HK. In an FDD system, each user estimates its downlink CSI matrix through pilot-based training and transmits the estimated CSI back to the base station. Hence, the overhead for CSI feedback from the users grows with K LC into NT and becomes prohibitive for wideband massive MIMO system when K, NC and NT are large. Next one, DeepCMC. In this section, we present our proposed neural network architecture, DeepCMC for encoding and subsequent reconstruction of downlink CSI for a single massive MIMO user. This will be extended to the multiple user MIMO scenario. The overview of proposed model architecture for DeepCMC is shown in figure, where the two channel input represent real and imaginary part of the channel matrix. The user compresses its CSI into available length bit stream. The encoder comprises a convolutional neural network based feature encoder, a uniform element wise scalar quantizer, and an entropy encoder. The feature encoder extracts key feature from the CSI matrix to obtain a lower dimensional representation, which is subsequently converted into discrete value vector. By applying scalar quantization, we have observed that the autoencoder structure does not produce uniformly distributed feature value and hence can be further compressed. Now, in this figure, we have proposed convolutional neural network architecture for the feature encoder and decoder in DeepCMC, where first layer represents a convolutional layer with 256 kernels, each of size 9 into 9, followed by downsampling by factor of 4, batch normalization and parametric rectified linear unit activation. The feature encoder consists of three convolution layers, the first of which uses kernels of size 9 into 9 and other two use kernels of size 5 into 5. The same padding technique is used such that the input and output of each convolutional layer have the same size. In this figure, we have convolutional architecture allows the use the same encoder network for any number of transmit antenna and carrier, while the feature vector dimension depend on the input size, which allow us to scale the CSI feedback volume with the channel dimension. The feature decoder at the base station performs the corresponding inverse operation consisting of convolution and upsampling layer. At the base station, the output of the entropy decoder is fed into the feature decoder to reconstruct the channel gain matrix. Similarly to the feature encoder, the decoder includes three layers of convolutional. The decoder architecture also includes two residual blocks with shortcut connection that is keep several layers with a plus denoting element wise addition. Next one is distributed DeepCMC. In a multi-user FDD massive MIMO scenario with K user, each user need to compress and feedback its downlink CSI to the base station separately. However, if the users are located close to each other, we expect their CSI matrices to be correlated as they share some common multipath component. The compression is carried out separately at the user. They can benefit from the correlation among their CSI matrix to achieve a better trade-off between the compression rate and the reconstruction mean square error. If the base station jointly reconstruct the CSI of multiple users from the received feedback message, this is motivated by the information theoretic result on distributed lossy compression of correlated source. To this end, we propose a distributed DeepCMC NN architecture in which a joint feature decoder is used to simultaneously reconstruct the CSI matrix for several users at the base station. Figure provides the overall block diagram of the proposed distributed DeepCMC architecture. According to this figure, a K-user distributed DeepCMC architecture consists of K separate encoder branches, each consisting of a feature encoder, quantization, and entropy encoder blocks to compress the downlink channel state information from user to K-bit stream. The feature encoder, quantization, and entropy encoder block architecture are the same as described for the single DeepCMC architecture. The point decoder and the bit stream go through K. Separately, entropy decoder with the same architecture as described in the previous section. The output of the entropy decoders are input to the joint feature decoder. This is the figure for DeepCMC for multiple user scenario. And next one is distributed DeepCMC for two nearby user. Effects of the training scheme. The two users placed 60 cm apart in the indoor scenario with an NC subcarrier 256 NT antenna. The users are placed at location 5 meter and 4.4 meter 5 meter while the base station is fixed at the center. As a baseline, we also consider the normalized mean square error obtained by encoding and decoding the channel state information of the two users using two independent DeepCMC network trained separately for each other user. In this figure, scheme 1 represents training the whole network from the scratch 3 lakhs step, while scheme 2 corresponding to the initializing the network parameter to those trained for single user DeepCMC and fine tuning only for 30,000 more step. Here in this graph we can see according to this figure there is a negligible performance loss by the proposed low complexity training scheme 2. We highlight that to generate the result in this figure, scheme 1 has been trained for 3 lakhs steps, while 2 is trained for 30,000 steps. Hence, the proposed fine-tuning approach significantly reduces training complexity that with time without sacrificing its performance. This allows us to scale distributed DeepCMC to a large number of users. In the rest of this session, we only present results for distributed DeepCMC trained with the proposed low complexity fine-tuning approach. Next one is for effect of inter-user distance on the performance of distributed DeepCMC to represent the typical inter-device distance in this indoor scenario. In a 20-meter room, place user around base station 30 meter 16 90 centimeter and NT have 32 NC is 256. So in this figure we observe that showing that user benefit from this information transmitted by each other despite distributed encoding. The performance improvement by distributed DeepCMC becomes more significant in the low bit rate region. The improvement also increases as the user get closer to each other. Next, now distributed DeepCMC for more users. In the performance of distributed DeepCMC with more than 2 users, a cluster-based distributed DeepCMC approach for efficient CSI feedback in FDT MIMO of DM system rate. NMMSC improvement by distributed DeepCMC depend on the number of users decoding jointly their relative distance and general system environment specific characteristic. With clustering, overall complexity becomes affordable while benefiting from the most significant amount improvement by joint decoding. Base station can using single user deep CMC for all users separately. This is clustering based. Here we can see that the base station can default using single user DeepCMC for all users separately. During operation of the MIMO system, whenever small cluster of the new user joining to the network, the base station can switch to distributed DeepCMC to improve overall rate, normalize mean square error performance. Now conclusion. So distributed DeepCMC can provide further reduction in feedback overhead, particularly for nearby user, and proposed a low complexity training method for distributed DeepCMC that can reduce the training complexity and time with only minimal performance loss. Thank you.